Trying to see if the image quality gets any better, just wiping the camera. Okay, homework.
That's a reads.
Mm. You're very close. We'll talk about it. Second one. Absolutely.
Try erase markers, and I did it on my board. I was like, oh, I get it. And I didn't know on paper, but I looked at the first one, not the second one.
That's okay. So screen break is fine.
But I'm gonna come to office hours today about the second one. I'm gonna.
Ready. All right.
Ron has like probably coming.
Try to see the door.
I saw it.
It opens.
Yeah.
Okay. I guess the first set of questions is, yeah, how did people feel about the matrices, tensors? Is that beginning to make more sense?
No. I'm sorry.
That's I prefer honesty. Before we keep, striving forward and applying these curve metrics and beginning to understand the nature of space-time.
We should understand dot curves.
We should we should understand the mathematics behind it. So maybe we can take a few minutes here, just talk about some things that we're not getting. And if necessary, we can, I can on the fly change the lecture. So what are the things that we're not getting?
Just trying to figure out, problem one of the homework, and we'll talk about it.
Okay, so problem one of the homework said you have a vector A that goes to A prime. You have a vector B that goes to B prime.
Yeah.
You have a tensor T that goes to T prime. These are given. And this is given. What does this mean goes to?
Multiplied by some sort of rotation matrix or.
Right, yeah, so there's the transformation, and we call that a rotation matrix. You can always, we're using the words vectors and matrices and tensors sort of loosely here, okay? And what letter do we give this one?
You didn't get one in the problem, but I asked you about it on Slack and you said L.
L, yeah, that's what we saw when we did, for example, we just rotated our axes, right? Okay, so we called it L. So if we're a little more careful here, how would we write this statement from A to A prime? And I'm going to put a little bar over it so that we don't have any issues with subscripts and non-subscripts. So if I go like this, AI to AI, how do I relate those two?
Is it just multiplying by I, J, or L, I, J?
Where?
By the A bar?
On the A side, right? So I multiply this by I, J, like that? Is that true?
Yeah.
Yeah. Is that true? Look at it.
Oh, what? Okay. Yeah, the L, I, J.
Or is it,
Oh, wait, no.
indices?
The indices are wrong, right?
Yeah.
Good. That's right. Okay. So the same thing's also true here, right? L, I, oops, fuck. I, J, B, J equals B bar J, right? Okay. So now what do you do?
Find L.
Good. So how do I find L?
I Google rotation matrix.
No. That is absolutely a way to start thinking about the words in that order, but it's not what this is. So why would I give you two vectors?
I saw like for A, when you multiply it in, it's gonna be the first column and you'll get.
Ah, okay. Good, so you have some information based on the fact that when we think about vectors and tensors and all of these different things that we're talking about with math, this type of algebra that we're doing is multiple equations at the same time. So here, what the power, of course, is that there are three equations hidden here, and I'm representing them as one. And there are three equations here, and I'm representing them as one. And if you think about it in that context, then what you're really beginning to think about is, well, I have to find Lij, which means that I need to find 9 components, independent components, okay? So I will be able to get 6 of them because I have 6 equations, right? And now I'm fucked, right? Because now I'm missing 3. Is there anything in the whole world that can save us? No, Google will not help us here. What do you mean they're orthogonal? What does that mean? That's a fancy word to just throw out on Monday.
Yeah.
Means that when you multiply like Lij times the transpose of them, it has to equal the identity.
Right, so that was the definition of this weird word, this weird word orthogonal, right? So the definition of the word orthogonal meant when a matrix itself can be multiplied by its transpose, it's equal to the identity matrix. Or another way of saying that was that the inverse was equal to the transpose. And we made rotation matrices, we required them, in fact, to be orthogonal. Right? So the orthogonality of a matrix is part of this problem. So the fact that Lij is a rotation matrix, not just random matrix that I concocted, right, tells you something really important. Okay, so let's put that third piece of information. So orthogonality. I don't know if that's right, but whatever. Requires that L inverse is equal to L transpose. Right? And if you do your matrix algebra, that means I can move this to the other side, and this becomes the identity matrix on one side is equal to LTL. And how do I do a transpose?
Isn't it just swapping the rows and columns?
Like this, right?
Yeah.
Yeah, so you imagine that it's pivoting around an axis of the diagonal and it just rotates. That might be the right thing. In my mind, I don't hear it that way. Like that doesn't quite make sense to me. I'm more of a physical learner, if you haven't noticed that. And everyone does these differently, right? So like some people really like matrices because that's like how they think. Some people are like, that's fucking weird, right? So we're gonna try and overcome both of those. Okay, so this is another equation, right? And this will give us all of the necessary constraints to find L. Does that make sense? Once you have L, you should be able to transform T to T prime. And if you don't find that T prime is diagonal, you did it wrong. Make sense? Is that the only thing you didn't get?
Well, I will not get the second problem more when I do it more.
You will not get the second problem more?
I haven't started to not.
Okay. That does make perfect sense. I just needed to, it's a Monday. We drink more of the coffee, I'll understand my life better. We're gonna jump into a description of curved spacetime. And there are some examples that we can do today, especially about the summation convention, that I think maybe like we'll just get to that. We'll re-talk about the summation convention in the context of general relativity. And then I'm just gonna write like 9 or 10 examples on the board and you have to tell me whether they're right or wrong. And maybe that'll help us kind of like get an understanding of what's good and bad. Is that reasonable? And then if you find something that you're still not getting in a specific topic, just let me know. We'll do it at the start of Wednesday. Okay. All right, so you have been, you're very good students, I gotta say. You've hung in here, you know, while I was sick and trying to explain what a levi's Savita tensor was while not vomiting. But you didn't ask me a very important question. And I've just said this thing, you all just accepted it. Yeah, you trust me a little too much, right? And that's great, you know, that's, as an undergrad, you know, you're supposed to learn, oh, trust the professor, write down the homework, never ask a question. Now you go to grad school, and the thing that they want you to do is question authority and like look at a paper that's got 20 years of publications and be like, that fucking paper's wrong, and that's how you like make your mark, right? Okay, so you didn't ask me a very important question. And that question is, what do you mean by flat space-time?
I did ask that question. I literally asked you that.
Okay, so you said, what did you say?
You said, I said, what do you mean by flat?
And what did I say?
I don't remember.
So I think maybe I gave you and it's very true, I do remember this conversation, maybe we were talking about gravity like curving and like weight, like curving the matrix. I guess what I want you to think about today is there is a mathematical description for that statement. So you're right, you did ask me that question, I'm now remembering in my sickness haze. But specifically, what do we mean by that mathematically, other than just like a vibe of like, oh, trampoline, curvature? What part of the space-time is flat? So I'm going to show you two examples today, okay? And when we think about describing space-time itself, we're going to run into some stuff that feels a little wonky, and that's okay, because we don't really think in 4 dimensions very well. So hopefully we'll rewire some of our brains and end up more mathematically inclined to understanding what this space-time thing is, right? Because it's one thing for me to say, oh, space is curved, and it's another thing for you to feel like, oh, that thing has certain derivatives that represent curvature, right? Okay. Ready? Okay, so let's start with our Cartesian coordinates. What are the components of our Cartesian 3-dimensional space?
For this X, Y, Z.
There you go. So let's start with dx. Let's do dy. Let's do dz. Okay, and what's my 4th component here? Minus dt. Okay, and if I want to know how long a piece of space-time is, you add them,
Square them in?
you square them in. Good. That's called adding in quadrature. Just in case you need more fun terms today. Okay, so this is what? This is flat. Ambiguous, because we haven't defined what flat is in a mathematical sense. Let me do this different. Right? Okay, good. Now let's imagine a world that is different. So every point in this room can be described in a Cartesian sense. There is an XYZ that represents the center of my cup. There is an XYZ that represents where the phone is, etc. Right? But I now need to model it in 3 dimensions still, with time still, but I'm doing it for a star. And so what I would really prefer is spherical coordinates. So how do I convert this into a description of spherical coordinates?
Or theta.
Yes, yeah, okay, so let's do this, because we're gonna be very careful about it. So first, how do I convert X into a spherical? You don't have them memorized? It's okay, neither do I, that's fine.
Sine theta is the thing,
It's what?
like sine or cosine or.
Yeah, well, which one? Sine or cosine?
I-
Both. Ah, that's the tricky
And
one.
they.
So they all have R, right? That one we know.
Yeah.
Good. The first one is
Sine,
sine what?
theta,
Good.
Cosine theta,
Sine theta here as well. And here? Good. And here? Cosine what?
No.
Good guesses. Okay. So now let's work out the differentials. How do I do that? Let's do dz. You can do the dx's and the dy's on your own.
dr, for negative dr sine theta, d theta.
Yeah, so you don't need a dr if you're doing d theta as well, because we're doing chain rule here, right? So first we treat it as though it's a respect to to r. So the first term would be
Dr cosine theta,
very good. And the second term is?
minus r.
Good.
Sine theta.
Yes. Okay, so that's not so hard to do, right? And you can do the same thing with these, but there's more terms. 3 as opposed to 2. Okay, so let's look at putting these and its counterparts into here. So where does this get us? This goes to ds squared is equal to? What's the first one?
It's probably still in time.
Good, because we didn't transform time, right? Okay. And the second one? You may not know it, that's okay. It's gonna be dr squared. Okay, and then we're gonna have r squared d theta squared. And then we're gonna have r squared sine squared theta d phi. Looks weird, right? You tell me. Does it look weird? No, doesn't look weird to you at all, right?
I'm familiar with like the R squared d theta and the R squared sine squared theta.
Right.
I remember that, more concerned with something.
Good. So the time component stays unchanged. That's good. All of the spatial components are positive still. That's good. And ds squared here has, there's a transformation essentially. So I've gone from one coordinate system to another coordinate system. Okay, so let me ask you a question. Does this describe flat spacetime? Why, yes.
It's still the same space.
Because it's still the same space. This is a really important and non-intuitive answer, right? The first time I saw this, I was like, well, you said it's spherical, so therefore the space is curved. No, we're only describing it mathematically. So it's still this room. I'm just creating an origin here, right? For example, at the edge of the table and thinking about everything as being r away from it and then describing where those points are. right? And it's still just an element, some distance between 2 points, but described through a path that, has this. Okay. Let me show you another one. This one's a little tricky. All right. What does that describe? What?
I don't know,
Oh, okay.
I guess you are like changing the DB and stuff with the Y squared.
What do you mean by that?
That,
Is it this?
that is different than that?
It is different from this, yeah.
Yeah.
What does this describe though? Yeah, what does this look like to you? Does it look like anything you've just seen? Does it look like the line above it?
It does when you replace R with water. R with Y, with theta. And then get into the theta.
The same thing, right?
No,
No, it is the same thing. It is exactly the same thing. So all I've done here is I've created a new variable called dx, but that's our new time coordinate. And dt is the new spatial coordinate. What is the point of doing this very frustrating and annoying thing? One is because remember, we don't want to be married to the idea of x, y, z. We don't want to be married to the idea of d theta, d phi, dz's. It's really important here to start looking at the space-time metric as having here, anything with a negative is the temporal component of the metric. And here, anything in the positive region is the spatial component of the metric. And what we'll find out is that space and time can become mixed. So you could have a set of variables, u, that depend on both x and t, right? But this will be time-like in its interpretation, and this will be space-like in its interpretation. Does that make sense? Because again, when we think about ds squared, ds really represents what? What does the ds mean?
Length.
The length, right? So we have to understand, is this length 0 and we're talking about light? Is this length less than 1 and we're talking about things that we can experience? Is the length more than 1? And that's space-like separation, right? Okay, I know that was frustrating. Of course I trick you, I always trick you. Okay, tricking is what do they say at Halloween? Trick and treat. Just trick. Sometimes I'm nice. Okay. Okay, so this also describes what type of space-time?
Also flat.
It's flat, still flat. Flat, flat, flat. So far you haven't seen anything non-flat, right? Okay. This one here is a great coordinate system. This is your tried and true. This is like the one that you grew up with. Love it. This one here, maybe you have some poor relationship with, said some uncomfortable things at Thanksgiving dinner, right? But all coordinate systems have some problems. And what I mean by that is, even though we talk about this coordinate system, there are places where you can get multiple locations described by the same coordinates. Okay, so not every coordinate system is kind of unique, and they all fail to provide some label somewhere, right? Let me show you an example of this. We're going to use a two-dimensional plane. So here's the 2D plane. And in this 2D plane, we're going to be writing ds squared. as d r squared plus r squared d phi squared. Okay, so what does that look like? It's our 2D plane. Here's R, and here's phi. Right? We're okay with that? Do we like this plane? Yeah, that's gorgeous, right? You know, it describes all of flat board space to infinity, right? Any holes in it? Any place in which it does a poor job? Why the center? Okay. Okay.
No, but if you decided to-
Oh, it's just 0.
Yes, 1.0, right?
Parentheses 0 have like too many points.
So, yeah, what about where phi is 0? Describes lots of parts of one R,
Mhm,
right?
absolutely.
Shit, okay.
Why is that bad?
Well, it's a coordinate singularity. So anytime. Anytime that you don't have a unique description for every point in space, right? If two places can be described by the same point, that's what we could consider coordinate singularity. Let me show you an example of this that's more obvious. Okay, I'm gonna apply a mapping here, and you're gonna say, well, that obviously breaks it, and that's because I designed it to break it. I didn't design it. James Hartle did. Okay, so let's imagine that we transform our coordinates. We're gonna use this, which is a very rational, super reasonable coordinate system. What do you think about that? So R is now a squared divided by R prime.
And H is constant.
That is a constant, yeah, sorry. Okay. So this will take this new one. And we would write it like ds squared is equal to a to the fourth, that's just our constant, r prime to the fourth, all times dr prime squared plus r prime squared d phi squared. Good. What do we think? That's good, right? It's totally normal, totally standard.
That one is 0, the length is infinity.
Yeah, right? That doesn't seem very realistic. So what did I do here in this coordinate system? What did this transformation do?
That's 0.
Yeah, it basically inverts everything, right? So 0 becomes,
And infinity becomes 0.
very good. So this is fundamentally what's happening mathematically, right? We take zeros and we map them to infinity. And we take infinities and we map them to 0. So now the line element, ds squared, evaluated at the origin, is infinitely long. Right? You say to yourself, is that reasonable? Well, it kind of is reasonable, right? Because, you know, it takes an infinite length to go infinity distance, right? Okay, but this is a coordinate singularity. This is due to the fact that our coordinates here were mapped this way, right? Anything unusual happen if I use this space? If I'm like, let's say I write this space out, got my dr squared, got my r, bada bam, we're walking all around, going from point A to point B in this flat plane space. So I go from here to here.
You'd have to go from like. Transfer that infinity to like whatever.
What is this 0? From here to here. Here to here. Is this gonna give me a different length in this coordinate system here than it will in this coordinate?
Right.
If I go from this point here to this point here in this coordinate system, and I compare it to the same 2 points in this coordinate system, do they give me the same length? Does one give me a larger length? Does one give me a smaller length?
Smaller.
Is this one smaller? Is that what you're asking?
Because we got divided by the R so much.
Yeah, but it is multiplied by 8/4.
Wouldn't it mess up any coordinate system if you did that weird transformation?
You mean mess up?
Like, if you did that, if you said x equals a squared over x prime, would that make that x mess up as well? Like,
Yeah, I mean, if you divide by x, then the origin gets fucked up. Yeah. That's true. Is that what you're saying?
Yeah.
Yeah, I mean, this is designed, right, to make it, the infinities go to 0 and the zeros go to infinity. But remember what we said about coordinate transformations. We wanted ds squared to be what? Same for everything. We said that ds squared should be an invariant quantity under any transformation. And that includes coordinate transformations. Because even though we are describing the space from this point to this point with different mathematics, the length hasn't changed. Right? So which of these two is larger?
because you're saying they're the same,
They are the same.
but except it's 0 and infinity,
What?
it's separate.
Except, exactly, except at 0 in this one, and except at infinity for this one. But now do you see why they're connected logically? Because if you were at infinity, right, and you were trying to draw some line measure, of course it would be infinitely large, right? But nothing unusual or special happens in this coordinate system. This is still a flat coordinate system. It just has a tiny little hole. And it's an infinitesimal hole, because as long as it's not exactly 0, you'll get a length. Right? If you get, 10 to the negative 19 next to it, it's a big number, but it's still a number, right? Okay, is that reasonable?
Yeah.
Okay. So let's talk about the metric, and we'll talk about some summation convention. And then we'll do some of these example problems and just see how well we're understanding the summation convention as a whole. Does this process make sense? Okay, so I would like for you to write down for me. We're gonna describe a general geometry, and I'm gonna write the definition of ds squared. I think we've written this before, but I'm just gonna write it again. Okay, it's gonna be g alpha beta x dx alpha dx, sorry, dx beta. Okay, so this is called this is the definition. Yeah, certainly we'll use it in the context of 4 vectors, but this is the definition of the metric. Now, if you think that has something to do with the metric system, sorry, doesn't. If you think that it has anything to do with anything, it probably does. I just don't know what the historical context is here. Metric usually means measuring. So this is the way that we measure space-time. So maybe that's the historical implication, but I've honestly not read that part of my GR textbook close enough to understand it. Okay, so that just leaves one little question here. What is G alpha beta?
summing over?
Yep.
Would that be like whatever is in front of our partial,
What do you mean partials?
or our DR or DX and Y?
Okay,
See, what word would I use?
that makes sense, the things we need, like.
Well, what he was saying is like, when you think of these little DRs, these, I think of as like line segments, right? So these would be like coordinate segments. So here I have some variables that I'm summing over, and this tells you
Six or multiplied by?
what those things are multiplied. That's the most important part here, right? So if you will be so kind, on your notepad, please write G alpha beta equals, and I want a matrix here. So you have to have the right number of components. Don't tell your friend how many components you have yet. And I'd like it for the flat spherical coordinates.
We need to include the time chart. Wow.
All right, what's in the top left-hand corner? Yes or no?
I don't have it yet, but I feel like because the two coordinates are multiplied by each other, we're gonna have to do something to get them to be alone.
Because the two coordinates are multiplied by each other, what do you mean with that?
DX alpha and DX beta, when you sum over them, they'll both be there, so you need to get a way to have them be alone. Like up there, it's just DR sorted.
Right. So. Okay, so each of these components, right, so if we think about this as a vector. Right, what is this vector? If I'm writing in the 3D coordinates.
DT, DR.
dt, dr,
D theta, D phi.
d theta, phi, right? That's the way we're thinking about it. Okay,
What would be the good one? Top left, right?
is that true?
That's for sure.
Rest of zero is where?
It's along the road.
Oh, they're squared.
Yeah, they're square, right? So there's two of them.
So you really want stuff along the diagonal.
You tell me,
So the next one's
That's what I
one.
did.
the next one's one,
That's okay.
and then one again?
R
Along with
squared.
that.
Well, now we have real fighting.
I.
Let's do the easy ones. Let's finish out. Are there any zeros on the board?
Yeah.
You're saying zoom, and I don't really know what that means.
Across the road.
Here?
Yeah.
Here?
Yeah.
And here?
Yeah.
And here?
Yeah.
Yeah.
You sure about that?
Yeah.
Okay, here?
Yeah.
And here?
Yeah.
And here?
Yeah.
Okay, second round,
Zero.
more zeros.
Yeah.
This way?
Two more zeros across.
A lot of goose eggs. Alright, now it's contentious. So now discuss with your friend.
R squared.
Hey, you have to fight.
I think it's R squared.
R squared, D theta squared.
Why do you think it's one, genuine?
Where's the R squared gonna come from?
Previously, when we talked about this, we defined it as but really.
When did we talk about this?
Oh, no, we did talk about it, we did talk about alpha.
Oh, wait, I was here.
No, you're making a point, but I'm just like looking at the flat space-time function, and I'm just like, if we. That's why I have the -1, because it's gonna be -1 times dt squared,
Yeah, I just don't know how to get the R squared without.
and then 1 for dr squared, and then I'm thinking r squared times d theta squared. So that's why I have r squared. Because how else are you gonna get the r squared out of this, like, space-time function when there's nothing else besides like that g alpha beta, so I think it's r squared.
Okay, I hear that argument, I hear your argument, I hear your argument. Anyone able to convince anyone? No. You're stuck?
Yeah.
Okay, so the one you're thinking about is here. This is the Cartesian metric. And it just so happens that every metric will be defined by the coordinate system in which it lives. So what is this one? It has -1, 1, 1, 1.
Okay.
Right? And Rolando's idea with the R's, right, is necessary because I got all this extra junk in front. Right?
So on the bottom one would be like the bottom right, would be R squared, right?
R squared sine,
It's right.
yeah. So I'm gonna go R squared here.
You were right.
Yeah.
Okay.
Yeah, but
Now
you're
we're
wrong.
dealing with spherical, okay.
Yeah. So that's why I asked, right? Because we need to create them in every coordinate system. Does that make sense? Okay. And so this is called G alpha beta.
Spherical metric or something?
Exactly. Exactly right. Spherical metric, right? Or metric for spherical flat spacetime. And you just get to say these fun things, right? Like if you're fucking saying spacetime, you just feel like, wow, what kind of math am I learning today, right? Okay. So, what's the rank here? Nope.
Second.
Why is it second word?
Wait,
Oh,
what's that?
you can describe.
There's only 2 indices.
Around.
It is a 4x4 matrix,
Yeah, it is.
but it's a second rank. What?
Second grade.
Okay, so we're using all of our words today. Big words. Okay, how many independent components are there? Hate that word. Yeah. Nope. Nope. I like the guesses though, they're very good guesses.
What's independent mean?
Ah, what does an independent component mean?
I'm asking.
Yeah, so what does that mean? Okay,
I think independent math means they don't depend on each other.
yeah, that is what it means in terms of
Variables.
for sure.
I don't know what it
Here,
means.
yeah, so here what we're really thinking about is which of these are described entirely by the constraints of both flat spacetime and the coordinates that we've chosen. So what I mean by that is even though there will be multiple objects in this matrix that have the same value, there's only a few whose value have to be the same. And what I mean by that is you have some diagonal elements here, right? Alpha, beta. Those are the only places where non-zeros exist, right? But you will also see when we describe some of the properties of the metric that this element here needs to be this element here. Okay? So they could be non-zero, theoretically, they're not. But they need to be the same. It's a symmetric tensor.
So are those two dependent?
These, yeah, this is dependent on this, just like this is dependent on this. And it's not to say that if you churned one up, that the other is going to change differently. They're the same, because when they're flipped Tij equals Tji, right? That's the definition of symmetry.
Did you say there was 4 independent?
Sure, there's 4 along the diagonal, right? But then there's 1, 2, 3, 4, 5, 6.
I thought those were dependent.
Well, these are, right, mapped to here.
Yeah.
So you still have to define them as zeros. So you can either say that these are the dependent ones or these are the dependent ones, but usually you say Tij equals Tji. Right? That's the way to talk about symmetry.
Oh my
Isn't
goodness.
that stupid? They should both sides be independent.
No, because then you really would only have 4, but that's not true. You still have to define these.
They depend on each other. They're both dependent.
Yeah, so you pick one, the other side. and,
But if this was 1, this would be 1 automatically.
Yeah,
If this was 1, then this would be 1 automatically. So it's the same, right? It's the equality of qualities. So there's only 10 things that you have to pick. But in this particular context, we're really only going to have 4. Right? And as we talk about more space times, you'll start to see some recurring patterns. So you're already seeing something that I'm going to just hammer home over and over and over, right? Where is time? Right. That's the time length. Right, and that's space. Over there, where's time? Same. Can you convert the negative number here using a coordinate transformation? What?
No? Yeah. Did you just ask the question?
I wasn't finished. You're already ready to go. And I guess you're getting it just from the way that I'm asking the question. But the question was, can I convert the time-like component, which has a negative symbol? Can I ever get it to lose the negative symbol? You tell me. Because what?
can time go back, and she just said like, time can't go back.
That's not really the interpretation that I would use. That's sort of an entropy rule, right? That would like require some understanding of what we think. Right now, time is just a coordinate, right? I'm not giving any physical meaning to it.
Is it because the time like space like thing?
Well, it just comes from the fact that if this is unique here in one negative and then these are not, right? Then that choice of adding a negative here, right, and not adding them here will always be undoable. Right? You just multiply the entire metric by -1 and you get back what you wanted. Does that make sense? We could show this in an example. You can do it for homework if you want.
Sure.
I don't think you're excited about that.
You're saying you can make all of the space negative and the time be positive?
And then what would happen?
You just multiply by.
You'll multiply by -1, right? X becomes -x. Right? T becomes -t. Yeah, 4. Okay, or you could make like T becomes IT, where I is the imaginary number, and you get 2 of them, you get a -1 out. Okay, so let's talk about the summation convention. And then we're gonna do a couple examples, and then I think we'll probably get through enough of today. How are people feeling about some of this stuff so far? A little bit better, okay. So let me throw down some more summation convention. We're just gonna slightly modify what we've used before so that when we talk about 4-dimensional vectors versus 3-dimensional vectors, it's all gonna be chill. Okay, first rule, very straightforward. You've seen it before. What did I just, oh. So the locations of indices must be respected. Okay. Rule number 1. Superscripts describe coordinates. Subscripts. Yeah, this is all rule one. Describe vector components. So let me give you an example. Here is d x a, which we're going to define as partial of x a with respect to partial of x b prime, with a little bar on it, times partial of x. Okay. Did I talk about here? The let me give you it's not even in the chain rule, we're gonna have because you have coordinates on the top and bottom, you're gonna need to have an understanding that the vectors and the coordinate components don't always match up. Let me give you a different example. It might be better. This is gonna be confusing. I know this is gonna be confusing. We're gonna try our best. So 2 is that repeated indices. Sum. Right? You have that one?
Okay.
Repeated indices sum. It doesn't matter what they are. We've talked about free indices, we've talked about dummy indices. Okay. So I can write G alpha beta, A alpha, B beta. Right? And what does this mean in the context of the two things that I just wrote, these two rules?
G is a vector and the A's and B are coordinate things.
Yeah, so these are our vector components, right?
Yeah.
And these are coordinates. Right? You also saw this in the context of what we called covariant and contravariant vectors, where I'm allowed to trade. I can bring a subscript up or down, but I can only do that at the cost of what? A negative. So if I bring one of these down, I have to buy it with a negative sign. Okay. So these repeated indices sum here, so that means that I'm gonna sum these ones with this one and these ones with this one, right? And I hope that we saw this, what was it, Wednesday? I think we had a really good example with the Levi Ceviche where you just grab only the ones and the ones, the twos and the twos, right? We can get every term that way. Okay, so this is equivalent to that, correct or not? Good. And what about what if we do something like
That, would that A be still like a constant or not? If it's not even valid, we will respectively.
I think it's okay, cause you did it right there.
No, I didn't.
Well, they're both the X.
No, I'm looking at the.
Oh, I didn't notice they were both alphas.
And so it's a to the power of B and then,
So you won't sum over the V? I don't think you can.
Why can I not do this?
it's a free variable, that we use a free variable.
Or is it just that there's two alphas, I don't know.
Someone for the alpha. No, two alpha.
You're never allowed to use 3 indices of the same type. Never.
Is that rule 3? Or-
No, that's part of this rule. It's something that we've seen at the very beginning. But I'm just restating it right now. So maybe I'll just write it, right? No triple or more indices. Right? You might mean something else, right? You might have meant for this to be like a gamma. Right? And there might be other parts in it as well, or maybe you were multiplying by this, and then you had another one that was over here, and this was beta, alpha, B, beta, B, gamma, like that, right? And you're like, it's fucking cool, boys, what do you think?
Well, you didn't triple use index.
Yeah, dude.
Beta, alpha, gamma. It doesn't have 3 times. Oh, I didn't know that was, sorry, I thought they were separate.
No, I'm multiplying the whole thing is together. Yeah, so you're right, so on this side, right, it'd be chill, right, because imagine that you calculated some quantity, and you want to multiply this quantity by this quantity, but you write that in your homework. Now it'll be really confusing, right? Because which alphas go with which, so each alpha each indice either needs to be alone or in a pair. Okay, that's the second set of rules. Okay, and it further complicates because no summing between let me just write what that means. Is that okay?
That's just okay, because you have to double. Alpha.
So why is that not okay?
Well, because like. So when up, and down, is that referring to like the 2 subscripts being the same and the 2 super subscripts being the same? Okay.
So Isabel's right. These alphas are the problem because they're both subscripts.
So I mean, you could do one on top and one on bottom.
Means you have to. Right? Okay. That was rule 2. Rule 3 is about free indices. That's what's left over, and they have to be equal on both sides of the equation. So this is the description of the symmetry of the metric. that okay? Why is that okay? It seems fine. Yeah, so let's look up here. The super and subscripts, that's in the right position. Here, repeated indices, there aren't repeated indices on the left and the right-hand side, so that's good. They're not summing between them. The free indices here are the same, so I have the same number of alphas on both sides and the same number of betas on both sides. And that's the only thing about number 3. So both of these have free indices of alpha and beta on both sides, and therefore it's an equality. What this equality means is that the metric is symmetric. To that 10 times fast. So G11 here, right, or G00, however you want to think about it, is the same as G10, right? Sorry, let me say that again. G10 is the same as G01. They're both 0. Right? As long as we flip those individual letters, it's true for all of them. Right? Okay. You may have noticed that we are now using not IJK. Generally speaking, when doing, this is like maybe this should have been rule 0, but it's like a hidden rule 0. Greek letters mean that we're using a 4 vector space. And that, for example, alpha is 0, 1, 2, 3. Whereas, what are they, Roman numerals? Roman letters?
I know those are Roman letters.
I think that's right. Is that not right? Where do we get our letters from?
Well,
Maybe they're Arabic?
I know the numbers are Arabic, I don't know where the letters come from.
Actually, it might even be.
I think,
If you don't want to-
and it's not important. Okay,
We have 2 seconds.
what- Yeah, it's the Latin/Roman alphabet,
This is?
just our alphabet,
Our
A, B, C, D, E, F, G.
Okay. Yeah, because you're right that the numbers are definitely,
Actually, the Latin alphabet is missing J
that makes sense.
and every other letter.
When did we get J? That's funny.
Well, it's just so we can, yeah, there's a picture of the J. Alright, it's missing J, U, and W. I just noticed.
He doesn't talk about it in here. Okay. Tell me what you think about this equation. Everyone likes it? Raise your hand if you like it.
think it's fine, but he's acting like he's wrong.
How do you already know?
You just have mannerisms wrong.
Because I have tells for when I'm drinking. Okay, so what's wrong with this?
I think it's the alpha and the B.
And the new, right?
New.
Yeah,
Alpha,
it's-
new.
What is that? That's the third rule, right? That free indices have to be the same on both sides.
Yeah,
So we talked about dummy indices, that's these ones. Here's your dummies. So in the left-hand side, the dummies are beta, because they're repeated up and down. Valid, good, dummy indices checked out. On the right-hand side, you got gamma, top and bottom, they are checking out too, still dummies, still good. But my free indices on the left and right don't check out, and therefore this is a garbage statement. Okay, they have to be the same on both sides. Otherwise, you're gonna lose people, right? Okay, so now you know all of the rules. And all we're gonna do for the rest of the class is I'm just gonna put up like shit that you just saw, and you're gonna tell me whether it's valid or not. Okay, can I get rid of this?
Can you explain the first rule more? Cause I still didn't, or, actually, no, it's fine. It's just the example.
Yeah, I think it'll make more sense when we start to use it more, when you see what the components really are, right? It just is saying, the main thing that that is saying, the most important part of what that is saying is don't arbitrarily shift subscripts up and down. That's the most important part. If you get a component that has a piece up, it stays up for the rest of its life, unless you pay the cost of bringing it down with minus sign. Okay? Okay. Let's do a little test. First one first. Who's excited? Anyone? And don't shout these out, write them down for yourself. Write down your answer. What is it?
should be wrong,
Why?
because of that gamma, there's no matching gamma. The side, so you just have like a single free and you see a gamma on the right hand side.
Is that it? You agree, disagree?
I agree. Again, the beta as well.
What do you mean the beta as well?
It doesn't mean the same thing.
What do you mean it doesn't mean the same thing? Are you saying the beta here is the same as the beta here?
So like,
Just,
you're not summing across both DXs on the right side, so it's.
Ah. So not only do the actual values of gamma and beta, right, here, they're unmatched. Right, so you have a gamma that didn't appear on this side. So you had a free index on this side that simply wasn't even present here. And here, how many free indices do you have?
Zero.
Zero. So I have two free indices here and none here. So the free indices don't match. Would this be okay if I made this into a gamma?
Yeah.
Easy, right? Next one. All right, Isabel, what do you think?
I don't know if it's okay, because we didn't talk about like the actual. Like tensors, if you can change the names of them, but if B and C are the same thing, it's fine.
Good, right? So this in fact tells you that B and C have to be the same, right? That would be what that statement would be. Right? So the same type of math that we've used everywhere else is still valid here. So this would be saying, just like you're thinking, right? Like, okay, if I'm doing the double sum, then each component of B has to be each component of C. Otherwise, this is not a valid statement. Good. All right, next one. We're gonna learn some new symbols today. This is our Christopherson symbol. You'll learn about what that means later. But we're gonna do some fun stuff here. It's got 1 up here, and it's got 2 down here. Okay. What would that make it?
Two.
Third order.
A third rank. Very good. And now I'm gonna do something like this. All right, Reed. What do you think? You see a R looking thing?
Yeah, I'm just storing these things, so.
It's the Christopher symbol. But you can call that, I don't know. I don't know what you want. You can call it weird with an R. I can see the R now. I've never seen it as an R, but I can see it.
I can see that.
Listen, I don't know. It's just like your Christopher symbol.
I know.
It has a Greek name, but I don't know what it is. It's probably capital Rho.
Well,
Yeah, can you look up capital Rho? Thanks.
Really important.
the indices for that and K are both on top.
Ah, that's good, right? That's not good. Do you like it? Is this good or not?
Mm.
Not good. Not good because
Something
you don't do something where?
like if they're on both the top, and what is the other one?
Here and here, right?
Yeah.
Good.
But it's also a free index on the other side.
There's 2 reasons why it's invalid.
That's capital gamma.
There you go. Exactly what I thought. Okay,
But can you explain why this one doesn't work? Like,
read.
Yeah, because you can't, since the capital gamma and A both have that, like you see on the top, that would need to be summed over, you can't sum over them, they're both on top. Plus on the right side, make it 3 units.
okay.
All right, Rolando, whenever you're ready.
The validity of that statement, like it says that it's an equality, but you know, I'm sure if this is like correct in terms of like, metrics or something.
Okay. Does it break any of the rules?
Honestly, we have coordinates at the bottom and then vector complex at the top.
What do you think? Isabel? Why do you think it's okay?
Because all of them for different rules are fine.
Okay, but there's, on the right hand side, there's no free indices, is that okay?
Can't just set the equal to the, so it has to have the free index.
I'm asking very vaguely, is it okay for zero, does zero have indices?
No,
No. So is that an exception to a rule, or is that saying that I have to do something different? Can a vector be set to zero?
Yeah.
Yeah, can an identity matrix be set to zero? Yeah, can you set it equal to zero?
make all those ones zeros.
Yeah, you can do that, right? So you could take any set of equations and set them all equal to zero. So even though, right, you say, well, this is a free index, and this is a free index, and this is a free index, and there's no free indexes on the right, your first instinct might be like, oh shit, maybe that's wrong. No, but what this is really saying is this is describing something like 40 equations where all of their derivatives are zero.
So something, if both sides have indexes, their free indices have to match, but if one side's just a scalar, it's fine.
Yeah, right, that's another way to think about it. Well, if you have free indices on one side and you have a scalar on one side, right?
That's
Like-
fine.
No, because that wouldn't necessarily be fine. Let's say you used,
So if that equals one, it wouldn't be fine.
let's see.
Like, is it only true for zero or?
I guess, yeah, I guess it must only be true for zeroth rank tensors. I'm trying to think about it right now, because you could set them all equal to a constant. That would be fine.
Yeah.
Yeah, and you're saying
constant,
scalar and that's
scalar
the
is
same.
thing.
Yeah, that's exactly, they're exactly the same word. They're just breaking my brain.
Okay.
Okay, so this is fine, right? They can be set to a fixed value, right? Okay. Last one. Oh shit, no, I guess not. All right. Well, we didn't quite make it as far as I thought we would, but that is, I think, par for the course. Is this helpful at all? And there's like 9 more we can do. So on Wednesday, we'll just do the rest of them. But what I'd really like for you to do is, have a look at the homework, have a look at the work that we've done so far. And if you're feeling lost in any of it, let's just recover that material. Because we're gonna go into spring break and you're not gonna think about this material at all, probably. And then you're gonna come back and I want you to feel fresh and ready to learn about curved spacetime. Because honestly, there's very few things that you'll ever learn about in physics that are as cool as curving spacetime. Okay.